Disturb me. Right, last you had a question. Sodium carbonate titration in that one. Right. %25 of a solution containing sodium carbonate, sodium bicarbonate. Egana අපි හැදුවද? හැදුවා. ගණන් දෙකක් දුන්නානේ. නේද? එකයි දුන්නේ. Sodium hydroxide. මේක හැදුවා. Right. Sodium hydroxide, sodium carbonate. Video බලනකොට පේන්නේ නැහැ නේ. Sodium hydroxide, sodium carbonate, 25 of solution. Containing sodium hydroxide and sodium carbonate. These two. Right. 0.1 MHCl with that one. Yeah, right. Right. 0.1 MHCl with that one. Here it says, right, phenolphthalein as the indicator. So when the phenolphthalein is there, 30 cubic centimeters consumed. It's given like that way. Then methyl orange with that one. And further 12.5. Methyl orange with that another 12.5. It's given like that. Right. So here sodium hydroxide always fully ionized. Therefore, sodium hydroxide, right, with the HCl at once neutralize sodium chloride water. This thing happen in the presence of phenolphthalein, 30 mean, right? Sodium hydroxide HCl, sodium chloride water neutralization taken place. Then sodium carbonate with the HCl right? When the first drop take place here, right? So here the volume is 30. Sodium carbonate into sodium bicarbonate. Sodium chloride. For both of these, 30 consumed. It's given like that way. Then methyl orange added. After this one, methyl orange added and then another 12.5. Given like that way, no? Another 12.5. That means this process, sodium bicarbonate, HCl, sodium chloride, carbon dioxide, water. For this one, 12.5. That's the idea. If this one is 12.5, this smalls here. We have here also 12.5. Right? Right? If this one is 12.5, total is 30, that means this one is 17.5. Only that one. Right? If you take that decision after, simple. This one with that sodium hydroxide, this one with that sodium carbonate. හරිද? So to reach to this one, right, you should have the knowledge. මෙතන දැනුම ගොඩක් තියෙන්නේ. කරනවාද? අපිට ගාන ලේසි වුණාට සිද්ධාන්ත ගොඩක් තියෙනවා. Right? Awareness about this one. Right? Then the reactions. Right? Sodium hydroxide reaction. Neutralization happen first. Then sodium carbonate halfway neutralization. All those decisions with that one. Right? So using this one, using this one, right? If you do the calculation, you will get the answers. Sodium hydroxide concentration, sodium hydroxide, 0.07. Got that? 0.07. Fine. Then sodium carbonate concentration, 0.05. 0.05 moles per cubic decimeter. Right? Sodium carbonate 0.05. Terunada. Right? This one 0.07. Like that. Now into the same place, I will take this one also. Metika hari. Right? Ketluak nani. Into the same place, I will take this one next. Now this is all right. Sodium carbonate titration, all right. Right? Mixtures, all right. Like that way, right? If you have this kind of one. If you have sodium, say sodium hydroxide and ammonia mixture. Sodium hydroxide and ammonia mixture. If not, HCl and acetic mixture. Parallel to this one, right? A simple idea about this one. Right? You have this kind of mixture. If you do a titration with HCl, what happens? If you do a titration with sodium hydroxide, what happens? Okay. We'll think about that one. Right topic. Topic titration of a strong acid, weak acid mixture. Titration of a strong acid, weak acid mixture. Strong acid, weak acid mixture. I draw this one. Strong acid, weak acid mixture. Right. Sodium hydroxide here. HCl acetic mixture. HCl acetic mixture. Right. Now, if you think about the pH curve for this one, sodium hydroxide volume, sodium hydroxide. What type of plot we can have there? HCl here, acidic here, HCl strong acid. Because of that one, pH value will be very low. pH value will be very low, right? So I add sodium hydroxide, what happen? All HCl will neutralize first. Nothing happened to this one will neutralize. When this one neutralizing, what happened? This one is a strong acid, right? That's why earlier, right? When you are learning the things, I told you the pH 7, right? Strong acids, strong bases, weak acids, weak bases, conjugate acids, conjugate bases. Had that idea? This one neutralize mean only the weak acid. With that, what happened? pH value, very low value. Now at once rise up to this kind of value. Therefore, here we can have this kind of increase. pH increase. Right? Sharp increase there, right? If methyl orange in the titration flask, what happened? Methyl orange will sensitive to this one. That means after neutralizing all HCl, we can have one sharp increase. One sharp increase. With that one, right? Methyl orange give the color change. Then, if further sodium hydroxide added, what happened? Another sharp increase later. Okay. So, like this, another one. This is a neutralization of right HCl. HCl neutralization. This one, right? Acetic neutralization. So we are about this one also. Right? With the phenolphthalein, with the methyl orange, like that, if you do the titration. First neutralization, HCl, strong acid completely neutralized, can have color change, right? Then you can note that one. Secondly, this one. Okay? මේකත් මෙතන ඇඳගන්න. ලොකු notes දෙන්නේ මම මෙතන, right? මේ අමතර උගන්වන්නේ මේ දැනුමත් තියාගන්න. HCl neutralization, right? Here, if consider volume, right, that is actually both HCl and acidic both. HCl plus acidic. Both neutralized there. Second equivalence point. right? Here mark the methyl orange, phenolphthalein both. Methyl orange, phenolphthalein. Methyl orange and phenolphthalein. Right. Take another topic. मेरे मन नोट टिका देने होती है हम ऐसी नहीं गरंदे का देना titration of strong base weak base mixture titration of strong base weak base mixture strong base weak base mixture sodium hydroxide and ammonia strong base weak base mixture with the HCl. For that one we'll draw the curve pH curve. HCl volume here HCl at the beginning sodium hydroxide ammonia both so pH value very high because of the sodium hydroxide. Sodium hydroxide neutralization with that one. Sodium hydroxide, only that one neutralization. Right? With that, we can have a sharp drop there. Earlier, sodium hydroxide, sodium carbonate. If sodium carbonate also there, sodium hydroxide neutralization with that. Right? Small change, but that is not a sharp drop. If sodium carbonate here. But ammonia, weak base, right? There we can have a sharp drop. All sodium hydroxide over mean, right? This kind of one. That is when neutralizing what? Sodium hydroxide. Sodium hydroxide neutralization. Okay, now ammonia there. That one also neutralize. Right, then ammonia produce ammonium chloride like that. So in acidic range. This one. Okay. මේ දැනුම තියාගන්න. Mark this one in. Here sodium hydroxide ammonia. Both. Neutralization. Here only sodium hydroxide neutralization. Adina make. If phenolphthalein is the indicator, here, in the first step, we can have the color change. If methyl orange is the indicator, after completing both, can have the color change. right? take down this one. 25 cubic centimeter portion, 25 cubic centimeter portion of a solution containing HCl and acetic of a solution containing HCl and acetic is titrated with 0.1 m titrated with 0.1 m sodium hydroxide, 0.1 m sodium hydroxide in the presence of methyl orange, as the indicator full stop. It gives color change after consuming 10 cubic centimeter of sodium hydroxide. 10 cubic centimeter after consuming 10 cubic centimeters of sodium hydroxide. Another 25 cubic centimeter portion, is titrated with 0.1 m sodium hydroxide. 0.1 m sodium hydroxide in the presence of phenolphthalein. And given the color change after consuming 50 cubic centimeters of sodium hydroxide. Determine the HCl and acetic concentrations in the initial solution. Right? Right. You can start it before that one. Now, when you are given question like that way, right? You have to analyze that one in two ways. One thing is what are the components, right? What's the titration like that way? Take a sketch of that one. Volumes dala sketch එකක් ඇඳ ගන්න අනිවාර්යයෙන්ම. තේරුණාද? නැත්නම් ඔයගොල්ලෝ මගේ ඇරෙනවා. One thing. The other thing is then with that one, what happened to the pH? Imagine that one and take a sketch of that one. Then you decide with the methyl orange, with the phenolphthalein, what happened. තේරුණාද? මේ ඩයග්‍රෑම් එක අඳින්න ඕන මේකත් ඇඳ ගන්න ඕන. අපි කටු කඩදාසියේ. right? ඒ කරලා තීරණය කරලා ඊට පස්සේ හදාන්න. right? You can start it. This one now it is simple. HCl acidic, initially acidic, happen like this way. HCl neutralization, HCl acidic, both neutralization. Ten cubic centimeters here. Methyl orange phenolphthalein. 50 cubic centimeters here. 10 for the HCl, 40 for the acetic, like that. So in solving a problem, right? Necessary reactions, write them. Point note 4, right? HCl concentration. 0.4 times of that one here, 0.16. This one 0.04, this one 0.16, right? හරිද? right? तर මේ සංකල්ප දෙකම හරියට තියාගන්න. එකයි ඕන. As the next topic, හැමෝම හරි. හරිනේ? මේ ඉවර කරන ප්‍රමාණපති පාඩම් කරලා ඉවර කරන්න. නැත්නම් ඕගොල්ලන්ට පාඩම එක දිගට අල්ලලා යන්න බැරුව යනවා. right? Next I will acid base indicators over. මේ වැඩි ඉවරයි ඈ. Acid base indicators, right? pH calculations, all those over. Right? As the next thing, I will introduce this one, iodometric titrations. Once you learn this one, iodometric titrations, තවරක් මම කියලා දෙනවා. Because definitely you can have question from this one. In your paper somewhere there will be iodometric titration. ස්ථිර වශයෙන්ම තියෙනවා. Right? ලියන topic එක. Iodometric titrations. එකම වතාවක උගන්ලා තියෙනවා නැවත වතාවක් උගන්වගෙන යනවා. දැන් ඊට වැඩි ඔයගොල්ලෝ පරිණතයි මේක උගන්වනකොට තුන්වෙනි පාඩමෙන් ඉගෙනුවේ. Right? කරුණු ගොඩක් මම කියාගෙන යනවා ඔයගොල්ලෝ ටට්ටක් ගාලා එකතු කරගන්න. Right? Where we do the iodometric titrations. Right? When you have a aqueous solution, if it contains some sort of oxidizing agent, ඉතා හොඳින් අහගෙන ඉන්න. Oxidizing agent. Usually, maybe permanganate, maybe dichromate, maybe iodate, maybe ferric, maybe copper 2 plus, or an unknown one. If they give an unknown one, they will give you the details. This one pass into this one like that. Okay? එතන මේ reactions ඔක්කොම මම කලිනුත් දීලා තියෙනවා. ආයෙ තවක් අපි ඉක්මනින් ලියාගෙන යනවා. You know how to balance those, right? Any kind of this kind of oxidizing agent here. I want to determine the concentration of that one. Now, when you want to determine the concentration of this kind of oxidizing agent, right? There we conduct the iodometric titrations. Right? We have this kind of experiment in the last lesson. Right? Dissolved oxygen, DO, dissolved oxygen. Right? Winkler method like that, we have method. Right? Winkler method. Last lesson, industrial chemistry, environmental chemistry, right? Dissolved oxygen. එහෙම නැතුව මේක වෙනම මෙහෙම උගන්වන්න කියලා නෑ කොහෙවත්. තේරුණාද? මම ඔයගොල්ලන්ට මේ ඩීටේල්ස් ටික දෙනවා. හරියට තේරුම් ටික දැනගෙන ඉන්න. අනිවාර්යයෙන් මේකෙන් ගානක් තියෙනවා. Right? So here what we do, right, when you want to determine the concentration, what we do, we take a known volume. Say for example, we'll take dichromate, aqueous solution. We take a known volume, say 25 cubic centimeters or 50 cubic centimeters, like that we take a known volume. Right? Then what we do, into this one we add dilute sulfuric. Dilute sulfuric to acidify the medium. දැන් කලින්ට වඩා පරිණතයි කියලා කිව්වනේ. ඒ කියන්නේ මම එහෙනම් තොරතුරු කියාගෙන යනවා එකතු කරගන්න. We want to acidify the medium. Without acidifying the medium, this reaction won't happen. Dichromate into chromium 3 plus. Right? It won't happen, right, if you are not acidifying the medium. Reason is now acidification need there if you are using this kind of one, oxoanions, permanganate, dichromate, iodate, like that, oxoanions. To take this oxygen to the outside, it needs the H plus. In the medium, it needs the H plus to take that oxygen to the outside. So therefore, to take place the reaction, definitely acidification needed. Okay? Especially in where? When oxoanions are there. After then, into this one, we add excess of Ki. Excess Ki. Potassium iodide, excess of potassium iodide. When at excess Ki, what happen? Ki with the dichromate, I minus dichromate, acidic medium. Right, iodide pass into iodine, oxidize, dichromate into chromium 3 plus. So you can have the balanced reaction. Right, can have the balanced reaction. Dichromate to chromium 3 plus, iodide to iodine. Now here, iodine release, I2 produced there. I2 non-polar, right? Very weakly soluble in water, you know that one. But here we are using excess Ki. One reason to use excess Ki. One reason to use excess Ki is want to confirm this dichromate completely involved to the reaction. If dichromate remain here, our calculation is wrong. We want to confirm all dichromate in this one involved to the reaction. So to confirm that one, enough iodide should be in this one. If not, when you add the Ki, right, if iodide is not enough to take place the reaction, part of the dichromate will remain in the solution. So to confirm all dichromate over, to confirm that one need excess Ki. Another very special reason, that is here in doing the titration, iodine produced here. Producing iodine, actually iodine vapor, iodine gas, I2 gas, like that is possible to pass to the outside. Okay. So possible to pass to the outside mean our titration. Next, what you do? This iodine, we want to titrate this iodine with the thiosulfate here. With the thiosulfate, right? Before do the titration, iodine vapor possible to pass to the outside, but we can control that one. How? When iodine producing here, if excess Ki, I minus in the medium, so I minus also in the medium, then I minus I2 join together and produce I3 minus. I3 minus, like that, it become completely soluble. It become completely solution, right? So I2, I minus, right? It is like this way, I3 minus. Therefore, I3 minus mean I2 means same idea. In doing calculations, instead of I3 minus, if you use I2, no matter. Reason is this one here, when titrate this one with the thiosulfate, all I3 minus come to this side. Right? So this kind of process inside this one. Again, right? Directly we consider I3 minus mean I2. Same idea. Right? Total iodine in this one when you are doing a titration, right? Involved to the titration. But like this way, it becomes soluble. Because of that one, now no chance to pass the iodine vapor to the outside. But actually, when doing like this way, even right after addition of these two, if you wait, right here, if you wait for some time, if this one open and wait for some time, what happen? Part of iodine possible to pass. Therefore, in iodometric titration, usually what we do after addition of these two mix together, and after then, right, as soon as possible, we do the titration with the right thiosulfate, standard thiosulfate. But in some cases, we get a problem, that is after addition of these two, in some cases, we have to leave, right? We have to wait for some time. But you will lock in, because some of the reactions, dichromate, iodide, like that, some of the reactions, permanganate, iodide, like that, right? In some cases, the reaction is slow. It takes some time to complete. If you wait there like that way, problem, right? That is in this medium, excess Ki ion, therefore iodide is possible, right? Then iodide with the oxygen possible to take place oxidation, right? Aerial oxidation, like that way, right? Aerial oxidation possible to take place here, right? With that one, what happened? Iodide, part of the iodide in this solution possible to convert into iodine. If it happen like that way, now we do the titration with the thiosulfate, right? In this medium, possible to produce iodine by the aerial oxidation. Actually, we need the iodine by the oxidation like this way. With the aerial oxidation also, if give the iodine, what happen? Right? Excess iodine there. Then it is wrong. Therefore, now in one way we have to leave that one for some time to complete the reaction. Not in all cases, in some cases. Okay. But if you leave it like that way, area oxidation possible. They would avoid that one. After addition of these two, we close this one using a watch glass. You can close it. And we keep this one in a dark place. Right? Because to take place the aerial oxidation, sunlight support them. So to avoid that one, right, keep that one in a dark place. Right? Again, දැනුවත් වෙන්න සාමාන්‍යයෙන් අහන්නේ නමුත් right? එහෙම කියලා කිව්වොත් එහෙම මේගොල්ලෝ explain කරොත් එහෙම ගානකදී අපිට කලබල වෙන්න දෙයක් නැහැ. That is to avoid the aerial oxidation. Right? After completion of the reaction like that way, now reaction over, iodine produced with that I3 minus, right? Dissolved iodine in the solution mean what's the color? Dissolved iodine with the water, right? This one appear in right? Brown to dark yellow color, right? When producing this one, Winkler method එක practically කරද්දී කපාට මේක දුඹුරු පාට වෙනවා, right? Brown to dark yellow color. If lot of iodine there, actually we observe that one in brown color. Iodine ගොඩක් ප්‍රමාණයක් තියෙනවා නම් දුඹුරු පාට තමයි එන්නේ. Whole solution turn into brown. Right? If less extent of iodine, then it is dark yellow. Extremely small extent of iodine, it is pale yellow, like that. Now, iodine, all right. Now we want to titrate this one with standard thiosulfate. Standard thiosulfate solution, with that we do the titration. Right, in doing the titration, thiosulfate iodine titration, our indicator is starch. My titration indicator is starch. But there also we have a problem. What is that? Now, usually when you are doing a titration, what we do, we add the things. After then we add the indicator, few drops of indicator, and after that we start the titration. But here we can't do like that way. In iodometric titrations, indicator starch. One condition is it should be a newly prepared one. If not, we cannot observe the color change. The other condition is we add the starch, right, when the iodine concentration in this solution is very low. When the iodine concentration in this solution is very high, iodine and the starch together produce a permanent complex. Then cannot observe a color change. Because of that one, right, at the beginning we do not add the starch to this one. What we do, we add this one. Now the solution is in brown color. Right, before that one, have to prepare the burette and have to fill the burette with the standard thiosulfate. Then the setup is all right. At these two, then directly we start the titration. In doing the titration, what happened? Thiosulfate, iodine titration. Thiosulfate, iodine titration, right? Thiosulfate pass into tetrathionate S46, 2 minus, iodine pass into iodide. Okay, මේ රියැක්ෂන් එකත් ඔයගලගේ පේපර් එකේ අනිවාර්යයෙන්ම තියෙනවා. right? මේක මම කියලාම තියෙනවා කලින් ඉඳන්ම කටපාඩම් කරගන්න කියලා. කටපාඩම් කරන්න කියන්නේ මේක බැලන්ස් කරන්න ඔක්සිඩේෂන් නම්බර්ස් දාලා ඉන්න එපා. වෙලා යන අපරාධي. right? Here 4 because of that one, 2 here. Here 2 because of that one, 2 here, like that. Okay, this reaction. So here iodine release, we titrate that one with this one. When titration carry out like this way, what happen in this solution, the iodine concentration gradually decrease. Right, how you observe that one? Earlier dark, right, or brown color, dark yellow color, like that way, color gradually decreasing. We can observe here it's turned into pale yellow color. We say straw color, pale yellow color. Until this one turn into pale yellow color, we do the titration. Now we know when this one becoming pale yellow, right, we know, right, iodine concentration inside this one is very low. We know that one. So you notice that one, then into that one we add few drops of newly prepared starch. Then the solution turn into dark blue color. Okay, turn into blue color here. After then, now iodine concentration in this one is very low. So you know that one. Therefore, carefully you have to carry out the other part of this titration, right? Because when you add another 1 drop, 2 drops, like that way, what happened? Here you can observe the color change. Then make iodine ඉතාම අඩුයි කියලා අපි දන්නවා. Extremely small extent of iodine because it is pale yellow color. We know that one. Therefore, carefully add another 1 drop, another drop, like that way. Then at once this one turn into colorless. Blue to colorless. That is the color change. Okay. When this one become colorless, stop adding this one and notice the thiosulfate volume. Okay, that is how to conduct the titration. Right. So blue to colorless, this is color change, right? But be careful, right? In some cases, right, when they are asking the color change in this titration, right, we have special places. එක අවුරුද්දකදී ඇහුව structured paper එක right? ඔගොල්ලෝ ඒක කෙරුවා මං හිතන්නේ මට මතක හැටියට. Right? Dichromate. Titration given like this way. In that one, right, ask what is the color change in this titration. Right here, usually that is when you're adding this one, blue color disappear and become colorless. But in this one, you can see, right, chromium 3 plus is in the solution. Chromium 3 plus is in the solution, chromium 3 plus in aqueous solution, right, that is green color. Because of that one, when the, right, blue color turn into colorless, green color in the solution appear. Okay, because of that one in that paper, right, past paper. Then as the right? Color change, you have to write that one as blue to green. Not the blue to colorless. Right? Now, permanganate, no matter about that one. Mn2 plus, so it is colorless. We can take like that, but they have given this one. With that one, the color change is green, chromium 3 plus, because of that one. Okay. When the color change given here, right, stop adding this one, then with that one, you can do the calculation. Okay, how you do that one? Thiosulfate here, thiosulfate volume known. very නෑනේ කියලා දුන්නා. මේක එකපාරක් උගන්ලා තියෙන ඉඳ මම මෙහෙම යන්නේ. ඔයගොල්ලෝ දන්නවා. මොකද්ද කරනවා කිව්වේ ආපහු එක වතාවක් බලමු. Oxidizing agent, it is here, take a known volume, right? Take a known volume, then add acid, excess Ki. Acid, addition of acid is not essential, right? But if it is a oxoanion here, oxoanion, right, there it is essential. එක අවුරුද්දක ගානක් තියෙනවා පුතේ මේකේ concentration එකයි අහන්න. ගානේ අහන්නේ අවසානයේ මෙයාගේ H+, needed H+, asking. Right? So they can ask anything, no matter. Onikak. Right? So at this one, add excess Ki. Adding excess Ki confirm two things. One thing is, right, all dichromate or the all oxidizing agent involved in the reaction. One thing. The other thing is releasing iodine. We want to keep that one in soluble form. Right? Want to dissolve that iodine. Then take the thiosulfate standard solution, titrate with that one. Right? When doing the titration, earlier brown color, gradually convert to the pale yellow. We feel now the iodine concentration is very low. Right? At that moment, add the starch into this one. Then the solution turn into blue color. Right? Then few drops of thiosulfate with that, it become colorless. Okay. At that moment, thiosulfate volume consumed, take that one. Now, concentration of this one known. Because of that one, thiosulfate moles known. Half of that one iodine known. That iodine here, that one related to the dichromate. Then dichromate amount known. Dichromate amount, right, known. Amount known, volume is 25, right? So that much of dichromate in 25, they are in 1000 like that way. Dichromate concentration. AC very there? Any? So like that way, you can determine the dichromate concentration. හරිද? මේ ගාන අමාරු කරනවා පුතේ මෙන්න මෙහෙම. Right? Here, this is the usual method. No, now this is all right. ඔයගොල්ලන්ට මේක පුතේ reactions, if you can write the reactions, right? If you take the correct sketch like this way, volumes and other things, right? ඒ ටික correct විදිහට ලියා ගන්න ඕන, right? Correctly, if you take those things after then, right? It's a easy calculation. Stoichiometry නේ තියෙන්නේ. Stoichiometry වලට බය වෙන්න දෙයක් නැහැ නේ, right? So easily we can solve that one. But the calculation, if they want to convert this on a complex one, right? Usually they give that thing, right? That is this concentration, they will not give that one. This concentration, they will not give that one. So they will give the details like this, say experiment 1, experiment 2, like that way. In one experiment, they will explain all these things and they will give you the volume, say for example, right? We certain volume, say 50, not 20, like that way. Volume given. One experiment. Okay, volume given, but the concentration of that one not given. Then they will give you experiment 2 like that, another one. මේ experiments උත් මාරු කරන්න පුළුවන්. ඉස්සෙල්ලාම experiment 1, experiment 2, right? In experiment 1, the standardization, experiment 2, this kind of one. Sometimes experiment, right? One in that one, this one, then standardization of thiosulfate as a second step. කරනවාද? මෙතිල් ඔරෙන්ජ් ෆිනොප්තලින් ගණන් වලත් පරිස්සම් වෙන්න. සමාලාට steps දෙකම යන එක ඉස්සෙල්ලා දෙනවා. Both steps over. right? ඒක දීලා ඉස්සෙල්ලා ඊට පස්සේ දෙනවා එක step එකකින් කල එක දෙන එක. එන්න pH curve එක ඇඳලා තමයි තීරණය කරන්නේ. හරි? මාරු කරොත් එහෙම නැත්නම් අපි වරද්ද ගන්නවා. right? somehow the possible way is this one, that is here concentration not given, right? Concentration not given, then we had the problem, that is we cannot determine the thiosulfate. මේක තීරණය කරගන්න බෑ. ඒකට ඒගොල්ලෝ වැඩක් කරනවා මොකද්ද? They will give you another similar type of titration. Sometimes, right, the same component they use there. Now when I consider potassium dichromate is a primary standard substance. Primary standard substance, potassium dichromate. So they can use this one, right? We take known mass of potassium dichromate. Known mass of potassium dichromate. Say for example, m grams. M grams of potassium dichromate. Known mass of potassium dichromate mean exact amount there. Dissolve in water, prepare say 250 solution. From that one taken 25 into a titration flask. 25. Into that one, like earlier, same method, excess Ki and the H plus, dilute sulfuric. Right, after then titrate with the same thiosulfate solution. Thiosulfate solution. Here also volume, right? I will take this one as V2, right? Given. Okay, same titration again, like this way, but we do that one with, right, m grams of potassium dichromate, dissolve in water, prepare exact 250 solution. Then from that one taken 25. Okay, then titrate that one with the thiosulfate. Now the calculation is to the reverse. Here the calculation is to the reverse. How? Here we know the exact mass. So with that dichromate moles, we can determine here. කටු සටහන් ඇදීම තමයි වැදගත්ම කාරණේ. හරි? Dichromate mass known, dichromate moles known, that much in 250. Concentration මෙතන known නෑ, that much in 250. Therefore in 25 like that way. Dichromate amount in the 25. You can determine that one. Now you know the dichromate here. That means in the calculation, now we pass to the reverse. Dichromate known. When you know the dichromate with the iodine known. When you know the iodine, you know the thiosulfate. This one all right. Now thiosulfate known here. Volume known. Thiosulfate amount known mean thiosulfate concentration. Our calculation. Right? Right? ආමි බලන්නකෝ. In this part, this is a standardization. එතන අඳුර ගන්න ඕන question එකේ, right? In your question you are writing the standardization, this is the titration. This is a standardization, right? Known amount. Take there, so you know the amount, number of moles here, mass given mean, moles known. That much here, therefore in this one, you know that one mean, you know this one in the titration. You know this one mean, you know the iodine that should release. Make up it done now. Then you take that one and with that you determine the thiosulfate. Now you know the thiosulfate moles here. Volume given, therefore thiosulfate concentration. We take that thiosulfate concentration here and take that thiosulfate concentration to this one. Now you know the thiosulfate, therefore iodine. You know the iodine, therefore dichromate. ගාන ටිකක් දුරදි ගියවන වුණාම මොකද කරන්නේ? Standardization, they will give that one. තව ටිකක් මෙයා කරන්න ඕන. මොකද කරන්නේ? Here give, right, one titration that is with the dichromate. Here give a different one. Say instead of dichromate, potassium iodate. මෙතන ගොඩාක් වෙලාවට එන්නේ potassium dichromate, if not potassium iodate. ඔය දෙකෙන් එකක්. KiO3. හරිද? तर practical එක දැනන් හිටපුවාම මොකලන තේරෙනවා, right? Here you can identify, this is the standardization, this is the other titration. අතන මේක දුන්නාම තව reaction එකකුත් ලියව ගන්න පුළුවන් නේ. හරිද? Another reaction to balance, like that way they will give it. හරි? ඉතින් මේ ගණන් හොඳට අඳුනගත්තාම මේවා ආසාවෙන් හදන්න පුළුවන් ගණන්, අමාරු නෑ. වරදින්න තැනක් නෑ. Right? හැබැයි ප්‍රොසෙසන් වෙන්න sometimes here when given that 125, here 50, like that changes possible. ඒක ප්‍රශ්න නෙමෙයි අපිට. Right? Method is this one. හරිද? පැහැදිලිනේ? පොඩි note එකක් ගමු ඔය ටිකට. Reactions ටිකත් මම පොඩ්ඩක් මතක් කරලා දෙන්නම්. එච්චරයි. Right? දැන් මේක පුතේ අහලා තියෙනවා copper වලින් අහලා තියෙනවා තුන් වතාවක් විතර. Copper වලින්. තේරුණාද? Right, metal sample in that one, copper percentage. Right? ඔය AC paper එක බැලුවොත් මේක ගොඩ තියෙනවා හම්බ වෙනවා. පාසුවෙන් හදා ගන්න පුළුවන් ගණන්. Right? ලියන්නකෝ. Arithmetic titrations are conducted to determine the concentration of an oxidizing agent, in an aqueous solution. Oxidizing agent in an aqueous solution. Within a bracket, right? Oxidizing agents, examples: permanganate, dichromate, iodate, copper 2 plus, Fe3 plus, right? Such oxidizing agent. Then as an example, right? Determination of concentration of aqueous KiO3 solution. Aqueous KiO3 solution. In left side, you draw this diagram. Make undergone. dilute sulfuric, excess Ki, excess important, standard thiosulfate aqueous solution. Right. In doing the titration, starch at here. Starch as the indicator. Within a bracket, you can write near the equivalence point. Right? Is there not clear? No? Take a known volume of potassium iodide solution. Potassium iodide solution. Add few drops of dilute sulfuric. Add few drops of dilute sulfuric and excess of potassium iodide and excess of Ki. Excess of Ki. Fill the burette නැත්නම් මේ හැරීම මේ charge කරන වෙලාව මදි. Fill the burette with standard a standard thiosulfate solution. Standard thiosulfate solution. Titrate the solution. Titrate the solution until it turns into pale yellow color. Until it turns into pale yellow color. Add few drops of freshly prepared starch solution. Freshly prepared starch solution. Continue the titration. Until the dark blue color of the solution. Titration until the dark blue color of the solution turns into colorless. Dark blue color of the solution turns into colorless. Measure the consumed thiosulfate volume. Measure the consumed thiosulfate volume. Using the amount of thiosulfate consumed, using the amount of thiosulfate consumed, determine the concentration of KiO3 solution. Concentration of KiO3 solution. Leave line and write following facts. Following facts Karunu, are important in this titration. Following facts are important in this titration. List out these, right? List out the excess Ki, used to confirm, excess Ki used to confirm the completion of reaction. Confirm the completion of reaction. Within a bracket, you will write. Within a bracket, completion of oxidizing agent. Completion of oxidizing agent. Close bracket. And it is also very important. And it is also very important to keep the evolving iodine. Important to keep the evolving iodine in soluble form. In space soluble form. Right? There you better write this one. I2, I minus, I3 minus. Like this. Then write. Till next point, right? When the oxidizing agent is an oxoanion, underline oxoanion, it is essential to acidified medium. It is essential to acidified medium. Essential to acidified medium. In here, adding H plus, is used to remove oxygen, to the outside. Take oxygen to the outside from the oxyanion. Take oxygen to the outside from the oxoanion. Next point. Examples examples. K potassium dichromate, potassium permanganate, potassium iodate. In such places we have to acidify. Potassium dichromate, potassium permanganate, potassium iodate. Next point. Sometimes, next point. Sometimes, after the addition of excess Ki, sometimes after the addition of excess Ki, it is needed to keep the mixture. It is needed to keep the mixture for some time. For some time to complete the reaction. To complete the reaction. In such cases, mixture kept in a dark place. Mixture kept in a dark place for few minutes. Post open, right? Mixture keep in a dark place to avoid. Mixture keep in a dark place to avoid the aerial oxidation. Dark place to avoid the aerial oxidation of iodide ions. Aerial oxidation of iodide ions. Everybody ලියමු aerial oxidation එක. Iodide into iodine. Iodide to iodine. Balance කරගමුකෝ. 2 iodide, I2, 2 electrons. Right? Iodide to iodine. Then oxygen. Aerial oxidation. Oxygen. O2. 4 electrons. O2. 4 electrons. 4H plus. Two H2O. Right? O2, 4 electrons, 4H plus 2H2O. මේක මේ ඉලෙක්ට්‍රෝකෙමිස්ට්‍රි වල අපි ගිය සතියේ ඉගෙන ගත්තේ. සනසුරාදා නේද? මේකේ රිවර්ස් එක නෙමෙයි. This one 2H2O to that side oxygen. Right? පොඩි මතකයක් තියෙන්න ඕනේ හින්දා ඈ. Aerial oxidation මෙතන විතරක් නෙමෙයි. Some other places aerial oxidation possible places. Right? So you can take the net reaction. මේ දෙක දුන්නාම ඇතිනේ net reaction එක හදා ගන්න පුළුවන් නේ. First one multiply by 2 and take the addition like that. Next point. In these iodometric titrations, starch is added near the equivalence point. In these iodometric titrations, starch is added near the equivalence point. Full stop. Starch forms a permanent complex. Starch forms a permanent complex when the iodine concentration is high. When the iodine concentration is high. Therefore, starch is added. Therefore, starch is added when the aqueous solution reaches a very pale yellow color. A solution reaches a very pale yellow color. You want within a bracket stroke color. Stroke color. Last point. In these experiments, sometimes it is needed the standardization of sodium thiosulfate solution. Needed the standardization of sodium thiosulfate solution. Within a bracket, right? Within a bracket, when the thiosulfate concentration is not known. In these experiments, sometimes it is needed the standardization of sodium thiosulfate solution. Within a bracket, right? When the thiosulfate concentration is not known. Not known. Close bracket. In such cases, primary standard substances. In such cases, primary standard substances such as potassium iodide, potassium dichromate is used for the standardization. Potassium iodide, okay, or potassium dichromate is used for the standardization. Next line, most probably arithmetic titrations are used to determine concentrations of following solutions. Concentrations of following solutions. iodide process ටික විතරක් දෙන්නම් balance reaction එක දෙන්නම් වෙදදී practice කරන්න දැන් මේවා පුළුවන් ඔයගොල්ලෝ දන්නවා මේවා right what happened ලියමු අපි ටක් ගන්න iodide to iodine iodide to iodine balance කරද්දී පුතේ එකට ලියාගෙන balance කරන්න exchange method එක මම half fine එක දීලා තියෙන්නේ එකවරම ලියාගෙන මෙතන exchange method එකකින් balance කරගන්න right net reaction එක ලියා ගන්න වෙදදී practice කරගන්න දැන් ඔය ලියලා තියෙන්නේ මේ වෙනකොට net reaction iodide plus 5 iodide iodide plus 5 iodide plus 6H plus 6H plus then 3 iodine 3H2O 3 iodine 3H2O next the permanganate to Mn2 plus MnO minus Mn2 plus iodide to iodine iodide to iodine The other reaction, 2 permanganate, 10 iodide, 16H plus. 2 permanganate, 10 iodide, 16H plus. 2 Mn2 plus, 5 iodine, 8H2O. Next, the dichromate. Dichromate to chromium 3 plus, iodide to iodine. Right? Dichromate, 6 iodide, 14H plus. 6 iodide, 14H plus. 2 chromium 3 plus, 3 iodine, 7H2O. 2 chromium 3 plus, 3 iodine, 7H2O. ඔය ඉතින් ලියවන්න ඕනේ නෑ මම. මේ වෙනකොට පුළුවන් කමක් නෑ ලියලා තියමුකෝ. 2 chromium 3 plus 3 iodine 7H2O like that way. උතන පුඩි asterisk mark එකක් දාලා ලියා ගන්න. chromium 3 plus underline කරන්න. chromium 3 plus underline that one, below that write green. Below that one write color change in the titration is blue to green. Color change in the titration is blue to green. Blue to green. On bracket එක ලියන්න instead of blue to colorless. Instead of blue to colorless, it is blue to green. Right? Then ferric. Ferric. Ferric to ferrous. Iodide to iodine. Ferric to ferrous. Iodide to iodine. Balance reaction 2Fe3 plus 2Fe3 plus 2 iodide. Then products 2Fe2 plus and I2. 2Fe2 plus and I2. Next one, copper. Copper. Padi maladini copper. Copper in the copper case, copper 2 plus to copper plus. Iodide to iodine. Copper 2 plus to copper plus. On copper ke adhi kiwi. Copper 2 plus to copper plus. Iodide to iodine. Here a special thing happened. What is that? Now like this you can balance it and then with that you can do the calculation. ගාන හදන්න පුළුවන්. කිසි ගැටලුවක් නැහැ. But a special thing happened. අහලා තියෙනවනේ මතකයිනේ. This one, copper plus with the iodine, it produces CuI like that is a solid white precipitate. It's a white precipitate. So details දුන්නොත් එහෙම right? ඒ ගැන මතකෙ තියෙන්න ඕන. එහෙනම් balance reaction when you are taking that one to precipitate this one like this say we take another additional iodide here. Right? වැඩිපුර පාවිච්චි කරනවා. ලියන්න balance reaction එක. 2 copper 2 plus 4 iodide. 2 copper 2 plus 4 iodide. Then 2 times CuI plus I2. 2 CuI plus I2. Then put a megadi methana 2 iodide here, 2 iodide with that 2 copper plus and iodine. That one even all right. Stoichiometry වෙනස් වෙන්නේ right? මෙතන මම 4 iodide ගත්තේ මෙතනට iodine දෙකක් ගත්ත iodide. මෙහෙම ලිව්වත් right? 2 of this one. 2 Cu plus මේක නැතුව Cu plus and I2. So copper and iodine stoichiometry not change. ඒක වෙනස් වෙන්නේ නැහැ. නමුත් අපි මෙතන precipitate කරනවා right? CuI. So වඩා හොඳ මේක 4 iodide with that one. Right? මොකද ඒගොල්ලෝ ප්‍රශ්නේ කිව්වොත් එහෙම white precipitate given like that way. You better write this one, right? මේක අනිවාර්යෙන් ලියන්න වෙනවා ඔයගොල්ලන්ට. හරිද? Except these, right? මේව ඇරෙන්න. Some other kind of oxidizing agent, even all right. No matter. Other kind of oxidizing agent. Right? With that one, even we can do the calculation. If happen like that way, they will give you the reaction. A reaction එක දෙන්න පුළුවන්. හැබැයි balance නොකර තියන්න පුළුවන් ඈ. Components දෙනවා balance කරන්නේ නැහැ. එතකොට balance reaction එකද දීලා තියෙන කියලා check කරන්න ඕන. Right? පොඩි ගානක් හදන්න බලන්න ටක් ගාලා. Percentage of copper in a brass sample. In a brass sample was determined as given below. 2 grams of brass. 2 grams of brass was converted to 200 cubic centimeter solution. 200 cubic centimeter solution by dissolving in nitric acid. By dissolving in nitric HNO3 acid. Within a bracket, right? No, within a bracket, no free nitrate in the solution. No free nitrate in the solution. Close bracket. 20 cubic centimeters of this solution, 20 of this solution is acidified calone. 20 of this solution is reacted with excess potassium iodide. Is reacted with excess potassium iodide. Evolving iodine is titrated with 0.1 m sodium thiosulfate solution. 0.1 m sodium thiosulfate solution. 0.1 moles per cubic decimeter sodium thiosulfate solution. Consumed sodium thiosulfate volume is 25 cubic centimeters. 25 cubic centimeters. Determine the percentage of copper in the brass sample. Percentage of copper in the brass sample. Determine the percentage of copper in the brass sample. මේකත් ලියා ගන්න පුතේ. Following experiments were conducted to determine the concentration of potassium iodide, in an aqueous solution. Experiment 1. Under that one, right? 25 cubic centimeter of aqueous KiO3 solution is taken into a titration flask added dilute sulfuric and excess of potassium iodide and titrated the evolving iodine with standard thiosulfate solution. Consumed thiosulfate volume is 15 cubic centimeters. Thiosulfate volume is 15 cubic centimeters. Consumed thiosulfate volume is 15 cubic centimeters. Experiment 2. Experiment 2. 2.675 grams of solid KiO3 solid. Sample is measured. Dissolved in water and 250 cubic centimeter solution is prepared. 250 cubic centimeter solution is prepared. $25 cubic centimeter volume 25 cubic centimeter volume from this solution is transferred to a titration flask. 25 cubic centimeter volume from this solution is transferred into a titration flask. Added dilute sulfuric excess Ki and titrated the evolving iodine with the earlier thiosulfate solution. It consumes 30 cubic. Wait. Yes. It consumes 30 cubic centimeters of 30 cubic centimeters of thiosulfate for this titration. It consumed 30 cubic centimeters of thiosulfate for this titration. Okay. Determine the concentration of KiO3 aqueous solution. Determine the concentration of aqueous KiO3 solution. I mean the initial KiO3 solution, right? KiO3 solution. බලන්න හදන්න ටක් ගාලා. කියදා හරි හරිද පිළිතුර කී දෙන්නේ 0.025ද බලමු KIU3 මම පොටෑසියම් අයඩේට් මොලමෑස් එක දුන්නේ නැත් හොයාගන්න බැරුව ගියාද කීයද බෙදුවේ 214යි හරිද එහෙම නේද බෙදුවේ potassium iodate iodine 127 මට ඒක අමතක වුණා මේ දැන් හදලා දුන්නේ ගාන එකයි potassium 39 127 and 48 214 so 2.675 I give that one right 2.675 divide by 214 0.01 25 moles that is the potassium iodate moles KiO3 moles 2.675 grams given divide by the molar mass 2.675 214 with that you get this much of moles that much of moles in 250 0.0125 in 250 therefore in 25 taken there not 125 moles හරිද potassium iodate moles හරිනේ then potassium iodate moles 3 times of that one is the iodine moles නේද reaction එක දුන්නනේ මං කලින් නේද iodine moles 3 times of that one හරිද දරුණි හැමෝම හරිද potassium iodate moles stoichiometry බලනකො දීලා තියෙන reaction එක අර iodate produce 3 iodine like that way so iodine mean 3 times of this one I2 moles I2 mean 0.00375 iodine moles thiosulfate moles mean double of that one neither then you know the thiosulfate moles iodine right 2 thiosulfate like that way therefore not 75 thiosulfate moles volume is 13 thiazolate volume. දැන් thiazolate concentration මම කෙටියෙන් ලියාගෙන යන්නේ concentration. දැන් ප්‍රශ්නේ අවබෝධය තියෙනවනේ නේද? Concentration. Not 0.75 in 30,000. thiazolate concentration. හරිද? දැන් ඒ concentration එක අරන් යන්න පළවෙනි titration එකට. හරි? ගෙනියලා count කරන්න. හරිද? හා. දැන් ඉතින් ওই ගාන හදපුති හොඳට ගාන කටුසටහන ඇඳගත්තා නම් ඕගොල්ලන්ට ගානේ කටුසටහන හොඳට ඇඳලා නම් අහන්නකෝ පුතේ මෙතන මේ concentration හොයන්න නැතුව නම් ඕගොල්ලන්ට මේ තියෙන 30කනේ 15 half කර හැකියි. එතන අපිට ගාන හොඳට පේනවා අපි දිගෑරියනම් ගාන කටුවරකට දාසේ නේද? එතන 30ක තියෙන මවුල ගාන හැව්වා එහෙනම් 15ක නේද? භාගයයිනේ. එතනින්ම ගිය හැකියි. ඒතර එහෙම හැදුවා කියලා මේකේ ලකුණු අඩු කරයිද නෑ එහෙම ගන්න අහන්නේ මොකක්ද ඒගොල්ලෝ අපෙන් ඇහුවනම් thiazolate concentration determine the thiazolate concentration determine the KiO3 concentration then you have to determine the thiazolate concentration but they ask here then මම මෙතන ඇහුවේ මොකද්ද he ask directly the KiO3 concentration එහෙනම් thiazolate concentration හෙවීම අත්‍යවශ්‍ය නෑ හරි ඉතින් ටික කරන්න පුළුවන් නේ උත්තරය ආවේද 0.025 0.0025 නේද ආයි හරිද 0.25 0.025 බලන්න 0.25 moles per cubic decimeter මම මේ දැන් හිතලා දුන්නේ ගානේ හින්දා මම උත්තරේ දන්නේ 0.25 0.25 moles per cubic decimeter හදලා බලන්න right අනිත් calculation එකත් හදුවද නැහැ ඒකේ එන්න ඕන ඔයගොල්ලන්ට copper එකේ 80% is the answer copper percentage එක copper percentage 80% හදලා බලන්න should be 80% brass sample in that one copper percentage හරිද පොඩක් ඉන්න ඒකේ copper copper 63.5 ගත්තොත් වෙනස් වෙනවා මම මේ හදලා තියෙන්නේ copper 64 දාලා එතන මිස්ටේක් එකක් ඇති copper 64 කියලා ගන්න එහෙම වුණොත් එහෙම පොඩක් 63.5 ගත්තා නම් වෙන උත්තරයක් එනවා පොඩි වෙනසක් හරි ඒක දහන්න කි right 64 ගත්තොත් 80ක් එන්නේ 63.5 ගත්තොත් පොඩි වෙනසක් ඊට වැඩි අඩුවෙන් එනවා පොඩ්ඩක් හරි එක් කරගන්න පුළුවන් නේ පොඩි අමතර කාරණයක් ඔය කියලා දුන්නේ iodometric titrations right ඒ ටික හරිනේ අවබෝධය ඕන දැන් ප්‍රශ්න කරන්න තියෙන්නේ ගණන් හදන්න පුළුවන් එහෙනම් හරි පැයක් තියෙනවා ලියන්න ටොපික් එක ionic equilibriums arise arise කියන කබල ලියන්නකො produce කියලා ionic equilibriums produced by very weakly soluble produced by very weakly soluble, very weakly soluble, within a bracket, sparingly soluble. Very weakly soluble, within a bracket, sparingly soluble. Strong electrolytes. Strong electrolytes. Right? Ionic equilibriums produced by very weakly soluble means sparingly soluble strong electrolytes. In electrochemistry, we learn strong electrolytes, weak electrolytes, non-electrolytes like that. Strong electrolyte mean how much dissolve in water. How much dissolve in water? Dissolving part should fully ionize. That's the condition. With that one, I told you silver chloride given a strong electrolyte. Reason? Silver chloride extremely small part dissolve. Extremely small part. That is why here we take that one. Sparingly soluble. Very weakly soluble. Strong electrolytes. Actually, here in this part, we will consider, right? Next ionic equilibrium, right? We consider about the earlier precipitates in inorganic chemistry precipitates, barium sulfate, silver chloride, potassium, sorry, barium sulfate, magnesium hydroxide, silver chloride, lead chloride, right? Copper sulfide, like that precipitates. Here we consider about that one. All they are strong electrolytes, but very weakly soluble. Now, when you consider sodium chloride is a strong electrolyte, well soluble one. Well soluble one. Highly soluble, strong electrolyte, sodium chloride. Silver chloride, very weakly soluble, strong electrolyte. Okay. So here I want to interest about that one. Very weakly soluble, sparingly soluble, strong electrolytes. එක අවුරුද්දකදී බහුවර්ණය කාලා තිබුණා. KSP concept is possible to apply. උත්තරේ මොකක්ද? Weakly soluble or sparingly soluble strong electrolytes. ඒගොල්ලෝ මාරු කර කර දීලා තිබ්බා. Highly soluble strong electrolytes. Weakly soluble weak electrolytes. Like that. So here weakly soluble strong electrolytes. තේරුණාද? We want to think about that one. Right? ඉස්සලා මේක ලියන් ඉන්නකෝ. In here we will consider about the very weakly soluble. We will consider about the very weakly soluble strong electrolytes. Very weakly soluble strong electrolytes such as silver chloride, barium sulfate, magnesium hydroxide, copper sulfide, CuS copper sulfide, lead chloride, PbCl2, etc. Right? Underline karana puthi very weakly soluble or sparingly soluble strong electrolytes. Sparingly soluble strong electrolytes. Next line. These electrolytes, when dissolved in water, extremely small amount of electrolyte dissolved in water. Extremely small amount of electrolyte dissolved in water. But the dissolving but the dissolving part fully ionize. Dissolving part fully ionize in aqueous solution. Fully ionize in aqueous solution. Right? All right. Now I will explain the concept under that one. To explain the concept, I use a different component, right? So anywhere you can, when you want to think about this behavior, right, you can use this example. But here I am using not the, right, sparingly soluble strong electrolyte. Instead of that one, I will consider well soluble strong electrolyte. That is sodium chloride. Man sodium chloride වලින් ඔයගොල්ලන්ට explain කරලා sodium chloride concept එක මං සිල්ලර් chloride වලට ගෙනියනවා. හරිද? ඒතර සිල්ලර් chloride වලින් හිතා ගන්න බැරි තැනක් වෙනකොට sodium chloride වලින් හිතන්න. හිතලා ඒක apply කරගන්න සිල්ලර් chloride වලට. හරි? ඒතර මේක හොඳට තේරෙනවා ඔයගොල්ලන්ට. Because sodium chloride, you know that one, you familiar with that one. Right? මොන බලන්නකෝ. අහගෙන ඉන්න ඕනේ ඉවර වෙනකන්. ඉතා හොඳින් ඈ. You take a water beaker. මේක බොහොම ලස්සන සංකල්පයක්. Right? Take a water beaker, into this one you add sodium chloride. Sodium chloride solid. Salt. Common salt, right? We dissolve. Add small extent of sodium chloride, mix it. Completely dissolve sodium ions, chloride ions. Another part added, mix it. That part also dissolve. Like that way, adding sodium chloride, mixing. Like that way, continuously when you are doing that one, right? Lot of sodium chloride will dissolve in this one. Lot of sodium chloride dissolve in this one. Okay. Somewhere after dissolving lot of sodium chloride, if you add further sodium chloride, when adding that one, it will mix with the water, dissolve. But you can identify in the bottom of this one now, right? Sodium chloride remain here, NaCl solid. Adding part dissolve, but a precipitation there. Where this thing happen after dissolving a lot of sodium chloride in this one. I add small extent, dissolve. Another part, dissolve. Another part, dissolve. Like that way, dissolving that one. Somewhere, right, we identify, right, after dissolving a lot of sodium chloride. Now you add sodium chloride. Adding part, dissolve, but a precipitation here. Sodium chloride remain in the bottom without mixing or without dissolving. Now you can take idea. This is the maximum sodium and chloride ion concentrations possible for that solution. This is the maximum sodium and chloride ion concentration possible for that solution. Okay, that is the maximum. We can say that is a saturated solution. That is the maximum possible to dissolve. So it is a saturated solution. So after the saturation, when you are adding further sodium chloride to this one, what happens? No way to dissolve further because it is saturated. Saturated means always the maximum. Maximum. So the other part precipitating here. Okay. Now maximum in this one, sodium ions and chloride ions. Other part dissolve here. Sorry, precipitate here. Okay. Now, say for example, into this one you add further water. Now adding sodium chloride, we stop that one. Into this one you add water. What happened? I add further water and mix that one. Then sodium ion and chloride ion concentration in the solution is, right, decreasing. Concentrations decreasing, diluting. When diluting that one, what happened? The part undissolved sodium chloride in this one, what happened? That will come to the solution. Okay, that will come to the solution. All right, say you are adding water with that one, all sodium chloride come to the solution. Okay, all come to the solution. Now water, if you add further water, now again it become unsaturated solution. Okay, if it is unsaturated solution, again if you add sodium chloride, what happen? Again I can dissolve certain part. එම නේද? මේ සාමාන්‍යයෙන් ප්‍රායෝගිකව දැනෙන දේ එකයි මම සෝඩියම් ක්ලෝරයිඩ් ගත්තේ. හරිද? පැහැදිලි? Now like that way sodium chloride, if it is saturated, precipitation possible here. If it is not saturated, further sodium chloride possible to dissolve. You imagine this one without changing the volume of this one, without changing the volume of this one, you have dissolved certain sodium chloride. Now it is a saturated one, but in the bottom you can see another part of solid. Without changing the volume of this one, I heat this one. What happened? I heat this solution. When heating that one, this undissolved sodium chloride will come to the solution. මේ දී වෙලා නැතුව තියෙන precipitate වෙලා තියෙන කොටසක් තියෙනවනේ. ඒ ටිකත් උඩට ඒ solution එකට. එහෙම නේද? සාමාන්‍යයෙන් අපි අත්දකින දේ. That one also comes to the solution. That means if you increase the temperature of the system, what happens? If you increase the temperature of the system, saturation appear with high concentrations. Saturation appear with high concentrations than earlier. කලින්ට වඩා සාන්ද්‍රණය වැඩි අවස්ථාවකදී තමයි සන්තෘප්ත වෙන්නේ. එහෙම නේද? හරිනේ? Anyway, if a precipitation here, definitely the above solution is a saturated one. On the ගණන් හදන concepts. Okay? Here precipitate is here. Precipitate is here mean maximum dissolved air. No way to dissolve further, that is why precipitate. Okay? Precipitation here mean this one is always a saturated one. Like I told you, right? If you increase the temperature without changing the volume, I increase the temperature mean another part of this one comes to the solution. Sometimes when heating that one, completely all sodium chloride will come to the solution. Okay? So under say for example at 50 degrees Celsius, at 50 degrees Celsius, the earlier part all come to the solution. Now it is soluble, all part is soluble. Say again if I allow that one to come to room temperature. Now saturation, under low temperature saturation appear with low concentrations. Mean again a precipitation possible. හරිද? now example එකකට කිව්වොත් for example lead chloride. තාටයක් ගුවන්ලා මම ආයි ගන්නම් lead chloride. In the case of lead chloride, that thing happen. You know, on heating, lead chloride dissolve, cooling, precipitation, like that way. Okay. Somehow, now I told you this one sodium chloride. We take a water beaker, into that one add sodium chloride, mix it, dissolving like that way. After dissolving lot of sodium chloride in water, it reaches to its maximum. Solution cannot bear more ions in that one. Therefore, what happens? Join together again and convert into sodium chloride solid. Right? So, sodium chloride solid possible here mean definitely the above solution. It is with the maximum ion concentration. No way to increase that concentration. Therefore, we say that one as the saturation. When saturated solution here, precipitation here. Then I told you, if you increase the volume of this one, when I am increasing the volume, concentration of the sodium ions and chloride ions. Concentration of sodium and chloride ions decreasing. When decreasing that one, precipitate here mean definitely this should be a saturated one. But I increase the volume with that, the concentrations decrease mean now saturation gradually disappearing because of that one. If a precipitate here, no way to appear precipitate while this one is not with the saturation. Make a saturation එකක් නැතුව මෙතන precipitate එකට ඉන්න අවසර නැත. එහෙනම් මම volume එක increase කරොත්, if I increase the volume, concentrations decreasing, no way to decrease the concentrations while having a precipitate here. Now what happened? Come to the solution. Sometimes all sodium chloride will come to the solution. Okay. So that is by increasing the volume. I told you another way, that is right? We have the solution precipitate here. You heat this one. On heating that one, sometimes all sodium chloride in this one will come to solution. Why that thing happen? Because if you increase the temperature, saturation appear here, saturation produce here in the solution with high concentrations than earlier. උෂ්ණත්වය වැඩි කරපුවාම සන්තෘප්තතාවයට එන්නේ ඉහළ සාන්දන වලින්. කලින්ටත් වඩා වැඩි සාන්දනයක් ආවම තමයි සන්තෘප්ත වෙන්නේ. තේරුණාද? That is the concept. Now, when you consider the things we interest here is what? Sparingly soluble strong electrolytes. Sparingly soluble strong electrolytes, in that one even the same concept apply. මේ concept එකමයි apply වෙන්නේ. ඒකයි මම ඔයගොල්ලන්ට කිව්වේ. කොහරි ගැටලුවක් වෙන වෙලාවට මේකෙන් හිතන්න මේක අපිට practical නේ. ප්‍රායෝගික දෙයක් නේ අපිට දැනෙන දෙයක් නේ. Now what happened there? You take silver chloride, water container, right? Silver chloride add into this one. Now the difference in the silver chloride and the sodium chloride is both are strong electrolytes. Both are strong electrolytes, but silver chloride is very weakly soluble. Sodium chloride is very strongly soluble. What is mean by very weakly soluble, very strongly soluble? What is mean by that one? Here sodium chloride come to the saturation with extremely high sodium ion concentration and chloride ion concentration. Here this one very weakly soluble, sparingly soluble mean this one come to the saturation with extremely small concentration of silver ions and chloride ions. මේ දෙනක තියෙන වෙනස ඔච්චරයි. මෙයා saturation එකට එන්නේ, this one come to the saturation with extremely small silver ion concentration and chloride ion concentration. There what happened? You had extremely small extent of silver chloride. What happened? That part dissolves silver ions, chloride ions. Okay? Then with extremely small extent, what happens? Silver ion concentration, chloride ion concentration, like that way it come to the saturation. ඔන්න තියෙන පුළුවන් උපරිමයට ආවා. Okay? Reach the saturation mean the other all silver chloride what happened? That part will precipitate. අතර මෙයාගේ අරයාගේ වෙනසකට තියෙන්නේ. Their sodium chloride come to the saturation with extremely high sodium ion and chloride ion concentration. Here silver chloride come to the saturation with extremely low silver ion concentration and chloride ion concentration. In both cases the same thing happen. අනිත් සියලුම දේ ඒ හා සමානමයි. එහෙනම් මොකද වෙන්නේ? When you add the silver chloride, extremely small part with that, now these two, their concentrations with that it becomes saturate. After then adding all silver chloride, what happened? Precipitate here. So usually we say silver chloride is a precipitate. Reason is when you are adding silver chloride to the water with extremely small concentrations, for example silver chloride in that case 10 to the power minus 5, 10 to the power minus 5.00001. With that much of concentration, it comes to the saturation. In the case of silver chloride, I told that one. In some precipitates, sulfide, say copper sulfide, for example, like that way. In some cases, the concentration here and here, like that way, say copper 2 plus and sulfide. That concentration may be 10 to the power minus 25. Come to the saturation, we say 10 to the power minus 25, 10 to the power minus 25. Imagine, that means when you add in this one, almost all precipitate. Add කරනකොටම precipitate වෙනවා. අයියේ with extremely small concentrations come to the saturation. තේරුණාද? saturation appear mean all precipitate, other part precipitate. එහෙනම් මේ හැම කෙනෙක්ම දිය වෙලා සන්තුෂ්ත වෙලා තමයි precipitate වෙන්න ගන්නෙ. තේරුණාද? එතකොට මේ සන්තුෂ්ත වෙන්න පොඩි ප්‍රමාණයක් දිය වුණාට අපිට ඒක දැනෙන්නේ නැහැ. The other way, now when you consider copper sulfide, for example, on a product copper sulfide, for example, now extremely small concentration, all other precipitate here. දැන් මම මේක heat කරනවා. heat කරපුවාම extremely small part come to the solution and again saturate. දැන් අතනත් එක්ක compare කරන්න පුතේ. sodium chloride වල මොකද උනේ? ගොඩක් ඕනනේ concentration එක. එහෙනම් ඔක්කොම ටික දී වෙලා උඩට එනවා වගේ. හැබැයි සාමාන්‍ය precipitate එකක් අපි ගත්තාම මේගොල්ලන් සිල්ල ක්ලෝරයිඩ් නෙමෙයි විශේෂයෙන්ම දැන් සල්ෆයිඩ් එකක් වගේ සිල්ල ක්ලෝරයිඩ් ගත්ත එහෙමයි. චූටි ප්‍රමාණයක් අය දී වෙලා උඩට එනවා. extremely small part come to the solution. It is extremely small. Then we can't feel that one. Precipitate එක දී වෙනවා අපිට පේනවද? නෑ. හැබැයි ඔන්න අහන්න කල්පනා in the case of lead chloride, right, here the solubility of lead chloride is somewhat high. චූටක් වැඩි එයාගේ. අපි තව පොඩකින් values එක ගන්නවා. සිල්ල ක්ලෝරයිඩ් වලටත් වැඩිය lead chloride වල solubility එක පොඩක් වැඩි. එහෙනම් මොකද වෙන්නේ? heat කරනකොට dissolve වෙන එක අපිට දැනෙනවා. Because of that one all precipitate come to the solution. Like the case in sodium chloride, it is not a right. Lead chloride is not similar to the sodium chloride. Sodium chloride highly soluble, lead chloride sparingly soluble. But when compared with the other precipitates, අනෙත් precipitates එක්ක compare with the lead chloride වල solubility එක ටිකක් වැඩි. එහෙනම් අපි heat කරනකොට right the precipitate come to the solution, we can feel that one. අනිත් තැන් වල අපිට feel වෙන්නේ නැහැ හේතුව 10 රින 25ක් විතර තියෙනකොට concentration එක තව චුට්ටක් උඩට ආවා කියලා අපිට දැනෙන්නේ precipitate almost there. But actually small part come to the solution. අත්‍තරම ගත්තොත් චුට්ටක් උඩට එනවා. එන්නද? Same thing. You have this silver chloride precipitate like this way now. Here actually equilibrium there. මෙතන එහෙනම් තියෙනවා equilibrium. මොකක්ද equilibrium එක? Silver chloride solid right, silver ions aqueous Cl minus aqueous, this kind of one. Silver chloride precipitate, this one and this one join and precipitation, this one dissolve and silver ions and chloride ions, like that way equilibrium. Reversible process එකක් තියෙන්නේ. Right, continuously this thing happen. This one dissolve, come to the solution, this one precipitate here, like that. It's in equilibrium. Okay, that is why now when these concentrations are decreasing, this one dissolve. Now I add water to this one. I add water to this one, what happened? Concentration of silver ions and chloride ions decreasing. So to increase that one, this one, come to this side because this thing happened right at the saturation. මේක වෙන්නේ කොහෙද? Saturation එකේ තමයි වෙන්නේ. ඔන්න ඕක තමයි ගණන් හදන්න ඕන වෙන්නේ ඔයගොල්ලන්ට. Here a precipitate possible while having a saturation here. මෙතන saturation එකක් නැත්නම් precipitate එකක් තියෙන විදියක් නැත. හරිද? මේකෙන් හිතන්න. මෙතන සන්තුෂ්ටි වෙලා නැත්නම් පුතේ ඉලුණු ටික උඩට එනවනේ. තියෙනවා. හරිද? එහෙනම් කිසිම මොහොතක මෙතන precipitate වෙන්න බෑ මේ උඩ සන්තුෂ්ත නැත්තම්. හරිද? එහෙනම් at the saturation we have this equilibrium. තේරුණානේ? දැන් එතකොට මේකට apply කරන්න බැරිද relationship එක? sodium chloride වලට. Actually possible. මේ saturation එකේදී sodium chloride solid, sodium ions, chloride ions, like this way. මේකටත් තියෙනවා එක. But right, this is not useful in our right now. This is not useful, right? When we are doing the calculations, it's not so useful. Reason is sodium chloride precipitation. In any case, we are not discussing that one. අපි sodium chloride precipitate කරන්න කොහෙවත් use කරන්නේ නැහැ. හැබැයි ඔයගොල්ලෝ industrial chemistry වල in industrial chemistry, right, we learn the industries, different industries, right? In those industries, right, we do the precipitation. Now, for example, right, common salt in manufacturing process, in that one also precipitation happen like this way. ලුණු හදද්දි precipitate වෙන්නේ මෙහෙමයි. තේරුණාද? Now you have the sodium carbonate production, right? In that one, sodium bicarbonate. First, we take the sodium bicarbonate. You know, sodium bicarbonate is soluble, aqueous solution, but in the manufacturing process, we take the sodium bicarbonate to the outside. That sodium bicarbonate crystals. සන්තෘප්ත කරලා මොකද කරන්නේ? sodium bicarbonate crystals විදිහට තමයි production එක ගන්න එළියට. තේරුණාද? So how you do that one? A precipitation mean saturation after that one the other part. එහෙනම් ඕනම තැනක මේ precipitation එක වෙන්නේ කොහමද? saturation එකට ඇවිල්ලා තමයි පුතේ precipitation එක වෙන්නේ. තේරුණාද? ඒ ඉන්නනේ අපි right in inorganic chemistry we learn some of the right compounds say calcium hydroxide. I told you ඒ කාලේ මං කිව්වා calcium hydroxide may be a soluble one or maybe a precipitate. That depend on the concentration කියලා ඒ දවස්වල කිව්වා. හරිද? ඇයි? concentration එක වැඩි වුණොත් it comes to the saturation. With that possible to precipitate. If concentration is not enough, it will not precipitate. Then අපි කියනවා magnesium hydroxide is a precipitate. තරුණාද? අපිට precipitate කරගන්න බැරි නම් මොකද වෙලා තියෙන්නේ? That means the magnesium and OH minus concentration is not enough. Not enough. Right? Not in the saturation. තේරුම් ගත්තද? එහෙනම් දැන් බලන්න. With the temperature what happened? With the temperature solubility increase. Ion concentration need further ion concentration for the saturation. හැම වෙලෙම saturation එකට ඕන කරන ion concentration එකත් එක තමයි precipitation එක තියෙන්නේ. හරිනේ? At a high temperature saturation appear with high concentrations. At a low temperature saturation produce with low concentrations. Okay? So with that one, here the things possible to change. පැහැදිලි? එහෙනම් අපි කලින් ඉගෙන ගත්තු earlier in inorganic chemistry we learn barium sulfate is a precipitate. Right? Silver chloride is a precipitate. Magnesium hydroxide is a precipitate. Copper sulfide is a precipitate. Lead sulfide is a precipitate. All they are like this. So therefore, now precipitation, with that we discussed this one. Therefore, we apply this concept only for these weakly soluble or sparingly soluble strong electrolytes. But actually it is here also that one apply. ඒකම තමයි මෙතනත් apply වෙන්නේ. අපි මේවට apply කරන්නේ නැහැ, මේගොල්ලන් විතරයි apply කරන්නේ. ඒක හේතුව මේකෙදී විතරයි අපිට useful වෙන්නේ. මේගොල්ලන්ගේත් භාවිතා වෙනවා in the industrial process. හරිද? දැන් පැහැදිලිනේ? එතකොට දැන් ගෙදර ගිහිල්ලා අද මෙන්න මේක කල්පනා කරන්න ඕන. මේ behavior එක ලුණු ටිකක් කරාම වතුරේ දිය කරනවා වගේ. හරිද? මේක ඉතාම වටින සංකල්පයක්. හිතන්න හරිම ලේසි. මේකෙන් හේතුව අපිට මේක භාවිතයේ තියෙන සාන්ද්‍රණය නෙමෙයි. මේකෙන් හිතලා කරනද භාවිතයේ තියෙන සාන්ද්‍රණයෙන් හිතලා අතන්ට යන්න. With high concentrations here, with extremely small concentrations here reach to the saturation. ඒ කියන්නේ මේ දිය වෙනව නැද්ද නෑ කියන එක තීරණය කරන්නේ මොකෙන්ද? saturation එකට එන සාන්ද්‍රණය. Some come to the saturation with extremely small concentration mean they precipitate. Some come to the saturation with extremely high concentration mean they dissolve. හරිනේ? එහෙනම් ඔය හිතන්න ඕනේ. මම දැන් නෝට් එක පටන් ගන්නවා මෙතනින්. මේක නෑ ඔයගොල්ලන් නෝට් එකට. මේකේ. හරි? මේක ගෙදර ගිහිල්ලා ඉතලා බලන්න. right? I වතාවකට කියනවා අහගන්න චුට්ටක් මේකේ here dissolve that one, taken the saturation, then precipitation, add water, volume increase with that precipitated part possible to take into the solution. Into that one again sodium chloride, again possible to precipitate. If not, right, precipitate is here, solution there, precipitate is there, you heat that one, with that what happen? Right? If cooling that one, what happen? ඔය ටික ඔක්කොම හිතන්න ඕන. දිය කරගෙන ගියා, saturate වුණා, දැන් precipitate වුණා. දැන් ලුණු වන්න තැම්පත් වෙනවා. මම වතුර වැඩි කරනවා, එතකොට ලුණු ටික උඩට එනවා. හරි? soluble වෙනවා. තේරුණාද? soluble වුණා තවත් ටිකක් තියෙනවා කියන්නේ still the saturation is there. එහෙනම් තව ටිකක් වොලියම් එක වැඩි කරන්න ඕන. වැඩි කරපුවාම concentration එක අඩු වෙනවා. එතකොට තව precipitate තියෙනවා නම් ඒ ටිකත් උඩට දෙනවා. තේරුණාද? මේක දන්න දෙයනේ තේරෙනවනේ කියන දේ. දැන් ඔන්න solution එක saturate නෑ. It's not saturated. Again if you add sodium chloride, again I can dissolve certain part. ඔන්න තව ටිකක් දිය කරන්න පුළුවන් වෙයි. Right? Solution is with some sort of maximum concentration. Maximum concentration එකක් යට තියෙනවා. ඒ දක්වා දිය කරන්න පුළුවන් එතනින් එහාට බෑ. If I want to dissolve further, one condition is I can change the volume. එක්කම volume එක වැඩි කරන්න ඕන. volume එක වැඩි කරොත් concentration එක අඩු වෙනවා. එතකොට දිය තව ටිකක් දිය වෙන්න ඕන. හරිද? එතකොට amount එක නෙමෙයි පුතේ මෙතන බලන්නේ මොකද්ද? Concentration. Concentration is the condition here, right? තේරුණානේ? එහෙම නැත්නම් volume එක change කරන්නේ නැහැ. temperature එක පුළුවන් වෙනස් කරන්න. Temperature increase. තේරුණාද? Temperature increase with that further possible to dissolve. The temperature increase කරපුවාම dissolve වෙන්නේ ඇයි? Temperature increase with that solubility increase. Solubility increase mean in another way the saturation reach with high concentrations. උෂ්ණත්වය වැඩි කරපුවාම සන්තෘප්තතාවයට එන්නේ ඉහළ සාන්ද්‍රණ වලින්. උෂ්ණත්වය අඩු වෙනකොට සන්තෘප්තතාවයට එන්නේ පහළ සාන්ද්‍රණ වලින්. ඒත් මේගොල්ලන්ගේ මේ ඔක්කොම වැඩ ටික තියෙන්නේ සන්තෘප්ත වෙන සාන්ද්‍රණය මත. සන්තෘප්තතාවයට එළඹෙන සාන්ද්‍රණය මත තමයි තීරණය වෙන්නේ. තේරුණාද? එතන මේගොල්ලෝ සන්තෘප්තතාවයට එන්නේ ඉහළ සාන්ද්‍රණ වලින්, මේගොල්ලෝ සන්තෘප්තතාවයට එන්නේ ඊටාම කුඩා සාන්ද්‍රණ වලින්. දැන් ඇති. තේරුණානේ? මේකෙන් හිතුවා මේකට ගේන්න ඒ concept එක. right? අපි මෙතනින් පටන් ගන්නවා. Consider a saturated silver chloride solution. Consider a saturated silver chloride solution. Saturated silver chloride solution. ඕනනම් පුතේ ඔයා කොහේ හරි තැනක පැන්සලකින් ඇඳලා තියාගන්න sodium chloride solution එකක්. හරිද? ගෙදර ගිහිල්ලා පාඩම් කරනකොට ඒකෙන් සියල්ලම හිතලා දැන් මම මේ දෙන නෝට් එකේ ටිකට හිතන්න පටන් ගන්න. right? ලුණු ද්‍රාවණයක් ගැන හිතන්න. හරි? මේකේ සියලුම සංකල්ප ඔයගොල්ලන්ට ඔය ලුණු ද්‍රාවණයෙන් ගලප ගන්න පුළුවන්. සියලුම සංකල්ප. right? Saturated silver chloride solution. Draw this one. Left side. In front of that, and you can write the note. Saturated silver chloride solution. Silver plus aqueous, Cl minus aqueous, silver chloride solid. Right? Then here a equilibrium like this way. Temperature should be fixed. Temperature fixed. Definitely this one should be a constant because the rates, here also rates equal because it's in equilibrium. In front of that one, it's silver chloride solid. Silver plus aqueous, Cl minus aqueous. Then right, at a constant temperature below this. At a constant temperature, silver chloride produces an equilibrium. Silver chloride produces an equilibrium as above. Produces an equilibrium as above. Next line. At the equilibrium. At the equilibrium. We'll apply the equilibrium law. K. At the equilibrium, I will take like this, a K equilibrium. Cell plus aqueous concentration, Cl minus aqueous concentration, Cl chloride solid concentration. Equilibrium low. Then write at a constant temperature, concentration of a solid is a constant. Concentration of a solid is a constant. Right now. Then to next line, right? K equilibrium, this one. I'll take K dash. Then you take that constant also into this side. Make at mehat again. K equilibrium, K dash, Cl ion concentration, Cl minus concentration. Instead of these all constants, in here we write that one. K, capital S, capital P. Subscript that SP, KSP. Cl plus, Cl minus. Subscript S and P. Capital S, capital P, subscript. We call this one as another equilibrium constant. Solubility, KSP, mean solubility product of salt. Solubility product of salt. Dravita gunite. Right? A sigma can, right? හරි නේද? අපි KW derive කරා වගේ එකක්. Right? Solubility product of a salt. Solubility product of a salt within a bracket KSP. Product of a salt within bracket KSP is the product of concentrations of ions. Product of concentrations of ions in a saturated solution of a salt. In a saturated solution of the salt, comma, raise in a saturated solution of the salt, comma, raise to the appropriate powers. Raise to the appropriate powers. Raise to the appropriate powers. Underline saturated solution of the salt. Saturated solution. Raise to the appropriate powers. Right now, saturated solution. එතකොට දැන් මම KSP ලියන්නේ සෝඩියම් ක්ලෝරයිඩ් වලට. හැබැයි මේ concept එක sodium chloride වලටත් අදාළයි. තේරුණාද? For the sodium chloride even KSP concept is all right. But usually we are not applying that one. එහෙන තමයි අර කිව්වේ මොනවාද? KSP concept is applied for sparingly soluble strong electrolytes. Right? Take another example. Silichromate ලියන්න. Silichromate Ag2CrO4 solid. Right? Silver plus aqueous chromate aqueous. පුතේ පොඩක් අහන්නකෝ. මේක හැම වෙලේම ලියද්දි පුතේ මේ පැත්තේ solid එක ළමයි මේවා මාරු කරනවා. හරිද? මේ පැත්තට dissolve වෙන එක. නැත්තම් දැන් අපි KSP ලියද්දි මාරු වෙනවනේ. හරිද? ආ. මේ පැත්තේ ඉන්නේ dissolve part එක ඈ. මාරු කරගන්න එපා. KSP silver chromate ලියන්න බලන්න. KSP silver chromate silver plus aqueous concentration squared CrO4 2 minus aqueous concentration. Right? Below this asterisk mark. This KSP concept applies only for the sparingly soluble strong electrolytes. Sparingly soluble strong electrolytes. මට weak electrolyte එකට apply කරන්න බැරිද? No. Reason? In a weak electrolyte, dissociated part, undissociated part, both in the solution. Acidic ඉදන්නකෝ. Acidic, acetate, H+, all there. එන ඒ වලට බෑ. Should be a strong electrolyte. Dissolving part should fully ionize and deprecipitate. Okay? Right. Another point. Again, underline කරගන්න sparingly soluble strong electrolytes. Direct MCQ. Okay, MCQ එක. Another asterisk mark. KSP is another equilibrium constant. KSP is another equilibrium constant. And therefore, KSP depend only on is another equilibrium constant, and therefore KSP depends only on the temperature. Only on the temperature. Within a bracket, for a given salt. For a given salt, KSP value, it depends only on temperature. Okay? Means, say for example, this one. This KSP value, if say 25 degrees Celsius, 25 degrees Celsius, under that one, silver ion concentration, chromate concentration, if you take like this way, that product is a fixed value. This may be, sometimes this may be high, sometimes this may be high, sometimes these concentrations may be same, like that, right? Different relationships possible, but the condition is the product of that one, like the KW earlier. KW වගේම තමයි. තේරුණාද? Concentration product with these appropriate powers, right? That one is a fixed value if the temperature is fixed. එහෙනම් හිතන්නකෝ අපි සරල එකක් ගමු silver chloride. Silver chloride, silver ions, chloride ions, precipitation here, right? If I want, I can change the conditions here. For example, say I add into this one, I add silver nitrate. When adding silver nitrate, what happens? Silver ion concentration increasing. But precipitate here mean earlier saturation. දැන් මෙතන saturation එකක් තියෙන්නේ. තේරුණාද? If I add silver nitrate to this one, silver ion concentration increasing. But no way to increase that one. Then what happens? Part of that silver ions with the chloride precipitation. එතකොට silver ion concentration එක වැඩි වෙනවා. chloride ion concentration එක අඩු වෙනවා. මේක තමන්ට දැනෙන පිළිවෙලට ගන්න පුතේ ඔළුවට ඈ. මම මේක precipitation එක වෙනම කියලා දෙනවා. මම මේ දැනට මේ කිව්වේ. හරිද? මෙතන condition එක මොකද්ද? Ion concentration product is fixed. මේගොල්ලේ concentrations මට කැමති විදිහට වෙනස් කරන්න පුළුවන්. KW වලින් හිතන්නකෝ. Add a few drops of acid. H plus increase. H plus increase වෙනකොට OH minus මොකද උනේ? Decrease. Product is fixed. තේරුණාද? I like that way. Under any given condition, temperature condition, right? Ksp value of certain compound is fixed. හරිද? ඒක වෙනස් වෙන්නේ නැහැ. එහෙනම් once if you determine that one, after then you can produce different equilibriums in this solution. No matter. මේකට තව වෙන ඕන දෙයක් එකතු කරන්න පුළුවන්. හැබැයි මේ equilibrium constant එක fix. ඒක වෙනස් වෙන්නේ. හරිද? දැන් ඕනනම් මට මෙතනට මේකට ඇමෝනියා දාලා හිතන්නකෝ මේ සිල්ල ටික මං අරයි යනවා වෙන පැත්තකට. Another equilibrium produced inside that one. Like that, different things possible. ඔය මොනවා කරත් in here the equilibrium is fixed. Equilibrium constant is fixed. හරිද? තේරුණා? දැන් අපි කලින් ඉගෙන ගත්තනේ ඕනම aqueous solution එක KW relationship එක තියෙනවා කියන අන්න ඒ වගේ තමයි. Right. Examples. At 25 degrees Celsius, උදාහරණයක් ලියන්න. At 25 degrees Celsius, KSP silver chloride. KSP silver chloride. 1.2 10 to the power minus 10. 1.2 10 to the power minus 10. Unit silver chloride කියන්නේ silver ion concentration, chloride concentration. Concentration squared. Next, at 25 degrees Celsius, KSP silver chromate. එහෙනම් KSP දෙනකොට ඒගොල්ලෝ ගානක් හදන්න temperature එක definitely have to specify the temperature. කරනවද? temperature එක specify කරන්න ඕන. Right, silver chromate 1.6 10 to the power minus 12. 1.6 10 to the power minus 12. Silver chromate 3 terms there. terms 3ක් එනවා. units එන්නේ මෙහෙමයි නේද? Right now. Then on a KSP definition, right? Idea is all right. Next topic. ඊළඟ topic එක. Ionic product. Ionic ගුණිතය. Ionic product like the KW earlier. Ionic product. right? What is mean by ionic product? It means this one. හොඳින් අහන්න. You think about a water container. Into that one, I add extremely small part of lead chloride. ඉතා කුඩා ප්‍රමාණයක් lead chloride දැම්ම කිරිතන්. Extremely small part of lead chloride into this one. That lead chloride whole part dissolve in this one. Extremely small part. Whole part dissolve. Lead 2 plus equals 2Cl minus equals. Sodium chloride ඔළුවේ තියාගෙන සංකල්ප තේරුම් ගන්න. Extremely small part added, all lead chloride dissolved. දෙවුණා. Right? All dissolve means still not reach the saturation. Now in this solution, I will consider the lead concentration and the chloride concentration. And I write the relationship as you are writing the KSP. Now we are writing the KSP in the same way, equilibrium constant, right? Here I will write lead 2 plus aqueous concentration, Cl minus aqueous concentration squared. Okay, I take the product of that one. Now I will, I can write this one as the ionic product. මේකට කෙටි වචන නෑ IP ලියන්න එපා එහෙම එකක් නෑ. Right? Ionic product. So ionic product mean at the given condition, right? In the solution, if I concern the concentrations and if I take the product of that one. How you are taking that one, how you are writing the equilibrium constant in the same way we write it. Then we call that one the ionic product. හරිද? දැන් ඔන්න කල්පනා කරන්න පුතේ. I add extremely small part of lead chloride to this one, whole part dissolve. Certain ionic product. Right? Certain ionic product. Still not saturated, they have a certain value there. I add further lead chloride. Say further dissolve. Further dissolve the lead chloride. What happened to the ionic product? Ionic product increase. More than earlier. තේරෙනව නේද? I add further. I ටිකක් දියුණා කියමු. Ionic product further increase. Somewhere like that way what happened when I am dissolving the lead chloride, ionic product gradually increase and come to certain maximum. Come to certain maximum. What is that maximum mean? Reach to the saturation. Ionic product reach to the saturation, right? Lead chloride comes to saturation, mean the ionic product reach to the maximum. Mean ionic product equal to what? KSP. Reach to the KSP. තේරුම් ගියාද කියපුදී? At any moment in this solution, if I consider the ion concentrations and if I take the product, that is the ionic product. Okay. Now adding part completely dissolved mean ionic product still not reach the saturation, mean ionic product is less than KSP. Ionic product less than KSP mean not reach to the saturation. Then තේරෙනවද? Right? Dissolve further lead chloride mean ionic product gradually increase. Come to the saturation mean ionic product equal to KSP. Okay? Equal to KSP. Somewhere say the ionic product tend to be increased than the KSP. Tend to be increased than the KSP, I mean. They will give you some details. Say this one lead chloride, not as the lead chloride. Make lead chloride is it? Lead nitrate, certain volume, and HCl, certain volume mixed together. Whether a precipitation taken place in this one. Certain amount of this one, certain amount of this one, they have given that one. So you know the number of moles, concentration and the volume given. Mixed together, whether a precipitation taken place here. අපි අහනවා precipitate එකක් හැදෙනවද? Now what you have to do? with the given amount volumes with that lead 2 plus concentration, we take that one. මේ mixture එකේ solution එකේ right concentration එක ගන්නවා. Then you take the chloride concentration also like that way. Then you write the ionic product. And we check that one with the KSP. Now when you are taking the ionic product there, ionic product become more than KSP. We can say ionic product cannot be more than KSP. KSP will already in the bed. But here tend to be more than, right? When the යනවා KSP වලට වඩා වැඩි වෙන්න යනවා. But it cannot be more than KSP. Maximum is the saturation mean the KSP. එහෙනම් KSP වලට වැඩි කියලා අපි ගණන හදපුවාම පේනවා like the QC KC. එහෙනම් අපි කියන මොකද්ද? Cannot increase than that one, therefore a precipitation is here. එහෙනම් conditions තුනයි. Right? Ionic product. We count the ionic product. If it is less than KSP, still the solution is not saturated. If the ionic product is equal to KSP, it is saturated. If ionic product tends to be more than the, right, KSP mean a precipitation, part of the components precipitate. Part precipitate. Part precipitate mean the above solution. ගාන හදපුවාම පේනවා KSP වලට වඩා ionic product එක වැඩි කියලා. ඒ කියන්නේ කොටසක් වන්න precipitate වෙනවා කියලා කියනවා. Then the solution, precipitation possible, then the solution for that one again we can apply KSP. ඇයි precipitate වුණා කියන්නේ උඩ තියෙන solution එක is a saturated solution. තේරුණාද? දැන් මම අතන කියනවා මේ දෙන mix කරා ඔන්න ionic product එක ගත්තා. We have taken the ionic product. It is more than the KSP. mean a precipitation. හරිද? precipitate වෙනවා කියලා කිව්වා. එහෙනම් precipitation එකක් වුණා. දැන් උඩ solution එක. Above solution is a saturated one. For that one, if you take the ionic product, that is equal to KSP. A solution එකට ඒ solution එකේ ඉතුරු වෙලා තියෙන එකට මම ගත්තොත් ionic product එක ඒක කෙලින්ම KSP. තේරුණාද? That means in හරි නේද? In a saturation, right? In a saturation, always the ionic product equal to the KSP. හරිද? KSP I can write if a precipitation only. Precipitation එකක් තියෙනවා විතරයි KSP ලියන්න බෑ. ඒ කියන්නේ saturation එකට ඇවිල්ලා නම්. Precipitation එක පටන් ගන්න ලෑස්ති නම්. විතරයි KSP ලියන්න පුළුවන් නේ. හරි. එහෙනම් ඔය ටික ලියමු අපි. Ionic product under that one. If write the අද වැඩි හරියකට නින්ද යනවා. If write the ඒ දවසේ අවුලක් දන්නේ. Product of ion concentrations. If write the product of ion concentrations. Product of ion concentrations. For an aqueous solution, product of ion concentrations for an aqueous solution of an electrolyte within a bracket, right? Within a bracket, as we write the KSP, close bracket, then it is known as the ionic product of the salt. Ionic product of the salt. Next line. Consider an aqueous solution. Consider an aqueous solution of lead chloride. Aqueous solution of lead chloride. Lead chloride aqueous. Lead 2 plus aqueous. 2Cl minus aqueous. Then I make a one way in live. I one way live. Sodium chloride was a ඔක්කොම දිය වුණා වගේ. හරිද? ඔක්කොම දිය වුණා වගේ. ඒ වගේ lead chloride එකතු කරා ඔක්කොම ටික දිය වුණා. all dissolved. මේ අපි හිතන්නේ මේ ටිකක් කුඩා සීමාවක sodium chloride වලින් කිව්වේ හිතා ගන්න ලේසි වෙන්නේ. ලුණු ටිකක් වතුරට දැම්ම දිය වුණා. ඒ වගේ lead chloride ටිකක් එකතු කරා දිය වුණා. හැබැයි එකතු කරපු ප්‍රමාණය extremely small part. Right? මෙතන solid lead 2 plus ලියන්න. lead 2 plus 2Cl minus. Then write ionic product below that. Ionic product. Lead 2 plus aqueous concentration Cl minus aqueous concentration squared. Then write the ionic product gradually increases. The ionic product gradually increases when increase the ionic product gradually increases when increase the amount of that electrolyte when increase the amount of that electrolyte dissolved in water. Amount of that electrolyte dissolved in water. Right. Further dissolve mean ionic product further increase, further increase, further increase. That idea. Next line. The ionic product reaches to the maximum. The ionic product reaches to the maximum. Reaches to the maximum. When the solution reaches to ionic product reaches to the maximum when the solution reaches to the saturation. Solution reaches to the saturation. Full stop. If the ionic product tends to increase then the Ksp. Tends to increase then the Ksp. Then the part of salt will be precipitated. Will be precipitated. Okay. Limapi. Ionic product less than Ksp. In front of that one, right? Ionic product less than Ksp. Unsaturated solution. Unsaturated solution. Next line. Ionic product equal Ksp. Equal Ksp. Saturated solution. Saturated solution. Ionic product more than KSP. Ionic product more than KSP. Part of the electrolyte should be precipitated. Part of the electrolyte should be precipitated. Right? Other than not. කට්ටියත් අද අඩුයිනේ. පන්තියකුත් තියෙනවා තමයි. right තව concepts දෙකක් තියෙනවා මේකේ solubility කියලා topic එකක් තියෙනවා common ion effect කියලා topic එකක් තියෙනවා ඊට පස්සේ ගණන් හදන්න තියෙනවා ද්‍රාව්‍යතාව solubility and the ionic right solubility කියලා තව topic එකයි common ion effect පොදු අයන ආචරණය ලබන සතියේ ඒ ටික කියලා දීලා ගණන් ටික හදලා ඉවර කරනවා ඊළඟ සතියේ cation analysis ඉවර කරනවා සති දෙකක් යනවා හරි ලබන සතියේ සඳපන්තිය එහෙමම තියෙනවා සඳපන්තිය 9යි හමාරට කිට්ටු වෙයි ඈ කමන්නේ හරි හරි එන යන්න පුතේ